Hey everyone, today we are going to solve the LeetCode question LRU Cache. Okay, I think this question has two challenging parts. First challenging part is we have to keep access order of data because if we have data more than capacity, we have to remove LRU data. And the second challenging part is get and put functions must be on time. At first, I tried to solve this question with DQ because if we access some data, that data will be most recently used, MRU. So just put that data at the last place of DQ. If we want to remove LRU data, we can remove the first data in DQ. But problem is we cannot meet on time when we remove data from DQ. It seems challenging to meet the problem requirements using DQ, so I considered a similar data structure, combination of doubly-linked list and a hash table. This is a doubly-linked list I created. So we have prev node and the next node, so we can easily move forward and move back. And this is an input array. So first two is capacity, and next we have put operation, and we have get operation, and there is another put operation. So let me explain with this example. Okay, let's use doubly-linked list. So first two operation is put, so linked list should be like this, 1, 1. So this is node, and this is a doubly-linked list, so we can move any direction. And 2 and 2, like this. And the next operation is get 1. By coincidence, 1, 1 happens to be the head of doubly-linked list, but what if we want to access 2, 2? In that case, we would need to traverse through 1, 1 to reach 2, 2, resulting in a linear time complexity. But this doesn't meet requirement, right? We have to operate with O1 time. So to avoid this, we use hash table so that we can access any data with O1 time. So let me create a hash. So in Python, hash table is a hash map like this. And then key is so left side of number, so 1, and the value is this node, so 1, 1, and 2, and 2, 2, something like that. But actually, there is another problem. We can access any data with O1 with hash map, but since we accessed 1, 1, so 1, 1 will be MRU, most recently used. So we should reorder the linked list. So to do that, we have to access 2, 2, but accessing 2, 2 is a linear time, right? So not O1. So that is another problem. My strategy to avoid the linear time is that we will have dummy nodes at the first and the last place, so that we can access easily the first node and the last node. So let's create a dummy node. So let's say oldest, and pointing first node, and this is a doubly-linked list. And another dummy node is, let's say, latest, and pointing last node, and this is also doubly-linked list. To access 1, 1, just oldest.next. And to access 2, 2, just latest.prev, because all nodes has prev and next, so we can easily move forward and move back. And sorry, I realized that misspelling. Latest. Let's reorder the linked list with 1, 1. So first of all, keep previous node of 1, 1 and next node of 1, 1. So prev should be oldest, so dummy node, and next node should be 2, 2. Easy, right? And since we remove 1, 1, so 2, 2 will be the first place. So oldest.next should be 2, 2. So oldest is prev. So in the solution code, prev.next should be this next, so that we can connect like this. And this is a doubly-linked list. So prev, not prev, 22.prev should be oldest, right? So in the solution code, next.prev should be this prev, so that we can create like a doubly-linked list like this. Let's call that operation remove function. Then we have to put 11 at the last position. But wait, you may think 11 was already removed from the linked list because we connect all this to 2 like this. So actually, these links don't exist anymore. So we can't access 11 data. But don't worry, we have hash map to access each data. To put 11 data at the last position, so we use hash map and latest dummy node. So in this case, prev, so we create a prev and next again. And in this case, prev data should be latest.prev. That means 22. And the next data is latest itself. And we put 11 between 22 and the latest. I mean here. So prev.next and then next.prev should be 11, right? So connect like this and connect like this. And then 11.prev should be prev, right? So that we can connect like this. And this is a doubly-linked list. And 11.next should be latest, so that we can create a doubly-linked list like this. So now we connect like oldest and 22 and 11 and latest. So this link doesn't exist anymore. Let's call that operation insert function. Okay, just in case, let me visualize remove function and insert function. So this is a remove function. So we access 1. So this one will be the last position in the linked list, right? But before that, we reconnect linked list. So that's why we keep previous node and next node. And this next node will be the first position, right? So that's why prev.next should be next node. And from next node, previous node should be this dummy node, right? So that's why we connect like this. So this is a remove function. Very simple, right? And this is an insert function. So this one will be last position. So that means here. So to do that, we keep previous function, previous node. So that is 2. And next node, so that is the latest dummy node. So prev.next and next.prev should be 1, right? So we can create like this. And from 1, previous node should be 2, and the next node is latest dummy node. So we can connect like this. Looks good. So this is a insert function. So both function is actually very easy and simple. The last operation is put. So actually I didn't explain the detail for the first 2 put, just we connect like 1 and 2. So let me explain put operation. So if we don't have the same key, just add 3 to the hash map and to the last position in the linked list. So we use insert function. If we have 3, execute remove function, because this description set updates the value of the key if the key exists. So we should remove first, then add 3 to hash map and last position in the linked list. So we use insert function. So now we don't have 3, right? So that's why just add 3 to hash map and then insert 3 into the last position in the linked list. So in the end, after we execute insert function, so 1 and 3 and 3 and latest, and this link doesn't exist anymore. And at last, so we have capacity, and now we have 3 numbers, right? So that's why we will remove LRU data from the linked list and hash map. So LRU data is now 2, right? So that's why remove 2 from the linked list. So we use remove function again. And then after that, remove this 2 from the hash map. So in the end, so linked list should be, so remove 2 and all this, and 1 and 3 and the latest. Something like that. Yeah, so that is a basic idea to solve this question. So let's jump into the code. Okay, let's write the code. First of all, create a node class. So this is a doubly linked list. So def and init and self and key and var. And self dot key should be key and self dot var equal var. And this is a doubly linked list. So we have self, prev node, and first of all none, not node, none, and self dot next also none. So this is a node class, and let's implement init. So first of all, self dot, let's say cap equal capacity, and create a hash map, let's say cache, and then we create a dummy node like self dot oldest, and we use a node class, so node, and let me put 0, 0, and then self dot latest equal node and 0, 0. And then first of all, there is no data in the linked list, right? So that's why oldest dot next should be self dot latest, and self dot latest dot prev equal self dot oldest, right? And let's implement a get operation. So get operation is like if key in self dot cache. In the case, first of all, remove target node, right? So self dot cache and key, and after that, so this node will be the last position in the linked list. So execute insert and self dot cache and key. So we create a remove and insert later. After that, return self dot cache and key dot var. If not the case, we should return -1. Okay, let's create a remove function and insert function. So def remove and self dot node. So this is target node. So first of all, keep prev node and the next node. So prev and the next equal node dot prev and node dot next. And prev dot next should be next, right? And the next dot prev should be prev node. And that's it. Easy, right? And let's implement insert function. Insert and self and target node. So for insert node, insert function, so we will insert target node into the last position in the linked list. So we use our latest dummy node and previous node of latest dummy node. So prev dot not prev dot prev and next equal self dot latest dot prev and next node should be self.latest itself, and prev.next equal next.prev equal target node, right? And node.next should be next, and node.prev should be prev node. Easy, right? At last, so let's implement a put operation. So we need a space. Okay, let's implement put operation. So if key in self.cache, so in the case, we execute self.remove and self.cache and key. And after that, self.cache key, and create a node and key and value. So we add new node to hash map, and we also insert a new node into the last position in the linked list. So self.insert and self.cache and key. After that, if length of self.cache is greater than capacity, in that case, so we have to remove LRU data. So LRU equal self.oldest.next, and then remove that node from linked list. So self remove LRU, and then delete from hash map del self.cache and LRU.key. So it's a long algorithm, long code. So hopefully there is no bug. Yeah, so let me submit it. Sorry, there is a bug, just misspelling. So cache. Let me submit again. Yeah, looks good. And I think we meet time complexity for 1. And the space is order of capacity, I think. Yeah, so that's all I have for you today. Please support me with the actions such as comment and hitting like button. I'll see you in the next question.